So in this particular video, we are going to introduce the TLS. We have all the ingredients to learn TLS at the moment. We have hashing, we have cryptography, we have RSA, we have Diffie-Hellman. Everything is what we need to learn TLS. So we are going to introduce TLS, and without further introduction, let's get into the topic. Transport layer security, or SSL, TLS, all pretty much the same thing. We'll discuss all of them. So first, let's have a look at what we have learned so far and where we are at. So we have discussed two pillars of security, cybersecurity, and we are discussing the first pillar, which is cryptography. So inside cryptography, we have discussed the hashing. Then we have discussed symmetric encryption. Then we have discussed RSA and a related concept called DH. So one of the things we have observed about DH is, in the DH, we are not transferring any data. All we are doing is arriving in a common key, a non-data to both parties. They are not exchanging any information. It's like quantum entanglement. There is no data transfer, but there is some kind of similar correlation or key between both parties. On the other hand, RSA is all about transferring data. We can transfer data using RSA. Now we have a lot of ingredients as of now to understand a lot of things in the real world. First and foremost is the TLS protocol, probably the most important security protocol in the whole world. So we have almost all the ingredients to understand this protocol. We have the hashing, we have the RSA, DH, and finally the symmetric encryption like AES. These are the ingredients for TLS. And that's what we are going to do. We're going to have a peek into the TLS or SSL, which is the earlier name of TLS. So in the case of TLS, it is using pretty much all these things in the screen. For example, it is using the signing, so digital signature we have seen, using hashing and RSA, digital signature or digital signature algorithm, DSA. And then it uses key exchange. So we need these two things to securely exchange the key exchange. And once the key exchange is done, we use the symmetric encryption to transfer the actual data, AES. So key comes from here and algo is AES. So TLS uses something like AES for the actual data transfer. So this is kind of the relation. What is the use of hashing? We will see. We'll see why and how hashing and digital signatures are used in TLS. And also we'll discuss a type of document called certificates or digital certificates. It's nothing but a document or a file which is transmitted between the server and client, which has certain attributes and things like that, which we will see. And to understand fully how TLS or SSL works, you need to have a bit of understanding about DNS resolution as well, which we will discuss, how the DNS is resolved. So if you want to know more about DNS and networking in general, I really recommend my networking training. I'll be always giving you the essential background when we discuss the relevant topic. Now, being said that, let's try to understand the general idea of TLS. So TLS or transport layer security. So the scenario is you have a client, which is Alice. So we have Alice and Bob, server. Bob is a server. And then the whole internet. So we have the whole internet right here, or public network, if you know what I mean. So this is the public network. So Eve is the part of public network. Eve can see whatever is being sent through the public network. So first we are going to discuss just normal TLS, not MTLS. There is something called MTLS where the server authenticates the client as well. First of all, our objective is to transfer data securely between client and server, Alice and Bob. And every single thing which is being transferred between Alice and Bob is visible to Eve. But the actual information being transferred is to be protected from Eve. That's the goal we are trying to achieve here. That's the end result. So probably you might have already figured out by now, using all the algorithms we have learned, how to do this. But just pause the video and think about a solution if you want, using the algorithms we have learned so far, how we can achieve this. Now, the overall idea about the algorithm is, first, the client is sending a request to the server. We'll get into the details of it. But the most important information in this particular request is, what are the different cipher suites and versions of TLS it supports? Basically, telling the server the capabilities of the client. What kind of algorithms it understands. What kind of TLS version it understands. Basically, the maximum supported version of TLS client is sending. So that is the first request in the case of a TLS handshake. What we are going to discuss is a TLS handshake. Now, the response of the server, so this is the response of the server to the client. The response of the server is mainly contains the algorithms the server has selected. For example, AES 256, RSA XYZ, DH XYZ version. So it gives a response of selected algorithms. Definitely that is from the given list of client. Now, another very important information server is giving is the public key of the server. Public key and selected algorithms. That is the main part in the response. There is a hash of this thing is being sent along with the CNAME and things like that. We'll get into those details shortly. And this part is called server certificate. We'll get into that details. But for the time being, you can simply think of this as the public key of the server. Once the client has the public key of the server, what client does? Client generates a random symmetric encryption key and encrypt that key using this public key and send it back to Bob or the server. Now, that is the first secret part. So a random symmetric encryption key is getting generated to the client and being transferred to the server. So this packet right here is intercepted by Eve. Eve can see that packet. But the question is, can she know what is the random generated symmetric encryption key in the client? No, she can't. Why? Because she doesn't have the private key of Bob. Only with the private key of Bob, you can decrypt whatever is encrypted using this particular public key. Because of that, Eve is not able to decrypt the traffic. Although she has access to the complete information, she is not able to decrypt any of it. Now, what is next? Bob receives, or the server receive this particular packet with the encrypted session key or the symmetric encryption key. There are so many names for this thing. They call it session key, symmetric encryption key, AES key. But ultimately, the idea is remaining same, that there is a symmetric encryption key is being transferred from client to server, encrypted by the public key of the server, which cannot be decrypted by the outsider or the public network because the private key is needed from the server. Now Bob decrypts this particular session key with its private key and then on switch the communication to AES or any strong symmetric encryption algorithm. From then on, the communication start. So let me draw that in a different color. So this green color is a symmetric encryption right here. Whatever it wants to say, it'll say in the symmetric encryption. Now the main question is, why do we need to do this? Why can't we use RSA for everything? Also, where is DH is coming? We have learned DH, Diffie-Hellman. So let's take one question at a time. The main question is, why can't we use PKI for the whole thing? Why do we need to negotiate? By the way, this is called symmetric key negotiation or session key negotiation. Different names are there for this particular protocol we just discussed. Why do we need to do that? The answer is mostly practical reasons, performance reasons. This public key infrastructure or the RSA algorithm is very expensive to compute compared to something like straightforward AES. AES is symmetric. All the symmetric encryptions are very straightforward to calculate. There is a very high limit of data which can be transferred at a time using public key encryption, which means using public key encryption is not very practical. So that is a reason why we need to use the public key encryption to negotiate a session key or a symmetric encryption key and use that key for rest of the encryption. That is what is done in the modern TLS. Now, what about the other things? Where is a hash is coming? Where is DH is coming? So DH is for the key exchange. There are two options for key exchange, like I was mentioning before in the previous session. One is RSA, like I just discussed. Another is, of course, the DH way of negotiating a key. Both has its advantages and disadvantages, and both are used even today as we speak in certain cyber suits. But this particular step right here can be done in DH as well. In fact, it is the elliptic curve version of the Diffie-Hellman. Now, again, we need RSA for a particular reason. That is what we are going to discuss next. So let me erase this particular diagram and I'll explain one specific use case of the digital signature part coming into the TLS algorithm. So again, we have Alice and Bob. This is the private boundary of Alice, and this is the private boundary of Bob. And this is the public network where Eve is present. Very smart engineer, Eve, who can see everything between A and B. Now, Eve has a public key and private key. Pretty much Eve has everything Bob is having. Now, Eve is telling Alice that she is Bob, and she has intercepted every single packet Alice is sending to Bob. Similarly, Eve is acting to Bob as well. She's telling Bob that she's Alice. Alice is thinking that she is connecting to Bob. So this attack is called man-in-the-middle attack. Man-in-the-middle attack. It's a very strong kind of attack and very difficult to circumvent as well, because there should be a way to verify that Alice is talking indeed to Bob. So when you access google.com, how do we know that data is coming indeed from google.com and not from a third party in between? How do we make sure that is the case? So that is the place where the PKI infrastructure is coming into the picture, so-called certificate authority and things like that. So this is a problem we are trying to solve. How to circumvent man-in-the-middle attack. Is there any way to verify the information coming from Bob is indeed from Bob? So you might be thinking that you know the public key of Bob. How do you know that it is the public key of the Bob? It can be the public key of Eve unless you know Bob very well, which is not the case all the time. There are so many different applications out there, so many different websites out there. Can you keep the public key of all the websites out there or applications out there? No, it's not possible. So what is the solution for this? First, we need to understand the problem. The problem is the public key of Bob is not a well-known thingy. There are so many entities like Bob. And when someone in the middle act like Bob, there should be some mechanism to understand whether it's from Bob or something else. So that is where the certificate infrastructure or the public key infrastructure comes into the picture with certificate authority. So that's what we are going to discuss next. So there are two main concepts we need to understand here is 1, certificates, 2, certificate authorities or CA in short. There's a concept of intermediate CA, but I don't think that's very relevant for our discussion. We will just assume that it is CA. But normally CA sign only intermediate certificates and intermediate CA sign actual certificates in most of the scenarios. But let's keep that details apart. So these are the two things we need to get our head around. So what are certificates? So digital certificates are simply documents. What are the things it contains? Let's see what are the things it contains. It contains the public key. So the public key of the sender. It contains the public key of the sender. Then a digital signature. It contains a digital signature. This digital signature is signed by a CA. We'll explain what is that. So CA is the branch manager we've been talking about in the previous lesson when we discussed digital signatures. We'll discuss what this really means. At the end of the day, these are another set of certificates, but all in all, it has a digital signature signed by someone we really trust. Someone's public key is known to us. That is this particular digital signature. So it has the public key and it has the digital signature. Another important thing, it has something called common name or CNAME. So it is mostly the name of a host. Say for example, google.com. I'll explain what this is, but this is an important item in the certificate. Another important item is SNI. SNI is very similar to CNAME or server name indication. It also has multiple entries like this. Say for example, google1.com, google2.com. It can have longer names as well. So it is more flexible than CNAME. So it has more number of these items. There are so many other fields like thumbprint or the certificate, email, company name, a lot of other entries. We will see a certificate very shortly, but these are the main entries inside a certificate. The public key of the sender, then a digital signature signed by a trusted party or CA, then the CNAME of the certificate or CN, and the SNI. These are the important fields. There are other important fields. We will see them, but for the time being, these are the things we need to discuss and keep going. Now, what is the use of public key? As we know, it is used for encryption. Now, what is the use of this digital signature? So this digital signature pretty much tells us whether this public key and these things are tampered. And this digital signature is signed by a CA. So what is a CA? So CA is a set of public key we know. It is there in our computer. All computer has a list of CAs or list of public keys which we trust. They are called known CAs or well-known CAs. They are there in our computer, every phone, every device which needs a proper TLS verification has a list of CAs. Basically, they are list of public keys which are known to the world. Let's have a look at the available CAs in this particular computer right now as we speak, before we continue this particular discussion. So in the run in Windows, if you're in Windows, you can type the command certmgr.msc. So this is the certificate manager in Windows. Shows all the certificate in Windows. At the end of the day, certificates are nothing but files. So these are the CAs present in this computer right now. CA certificate. So trusted root certificate authorities. They are special certificates at the end of the day. Basically special public keys of CAs. So these are the different certificate authorities available in a typical Windows operating system. I'm pretty sure this will be same in Linux, etc. Now, any computer I'm connecting to and I'm going to trust has to be signed by this particular CA. This computer will not trust any other certificate coming from any other sources other than this list of public keys. So let's click one of them and have a look. So this is the look of a typical certificate. There is purpose and everything. They are certificate attributes. We will have a look into certificate, a little more detail. For the time being, this is how it looks. So this is a certificate authority, which is trusted. It is not signed by anyone else. It is kind of a a root certificate. This is also called a root certificate. Root certificates are not signed by anyone else because they are root. So certificate has version, serial number, and all these other attributes. And as you can see, it has a public key. Most important thing, especially for a root certificate, the public key matters a lot, because this is the public key we are going to use to decrypt the hash of other certificates to make sure that the certificate is not tampered. And these are the companies, these are well-known companies which we are going to trust. If there is a non-well-known company here in this list, it means that your computer is compromised for sure. These companies should be known, and these certificate should be known as well to you. So now that we have seen where we are saving the trusted root certificate or public keys which we trust, let's have a look at a couple of actual websites where this is getting used. So the main thing I'd like to try is SourceLens website. Let's have a look. So this is the SourceLens website with the certificate. There's a lock icon here, which means that the connection is secure. And if you click on that lock, you will get this particular menu. And when you click on connection secure, you can get more information about it. And if you click on that certificate, you will get here. And this is signed by or issued by. So this certificate is issued by this particular party, Cerigo. So this is the issuer of this particular certificate, and the C name is sourcelens.com.au. We'll explain all this flow shortly, but right now we are trying to understand what CA really means. Now if I go to this, it is a CA, and if I go to the details here, I can see the certificate signing chain. So this certificate which we are looking right now, which has a C name, sourcelens.com.au. That is the C name of this particular certificate, one of the most important fields in this certificate. And it is signed by this particular party or issued by this particular party. And that certificate, the one here, this one is signed by this particular entity. And this public key or this certificate, I'll be using the name public key and certificate interchangeably from this point of discussion, but it is not exactly same. Public key is just one field inside the certificate. Certificate has a lot of other things, but this particular public key should be trusted by this computer, or this lock item wouldn't have come right here. So this particular party should be present here in the trust store. Let's verify that. User trust RSA certificate authority. So this is our cert store, trusted root certificate in the cert MGR. So let's go for user trust RSA certificate authority. So this is that entity we have seen in the root. So we trust this guy. My computer, when I installed my operating system, I trusted this guy. And because of that, I trust this guy because this guy is signed by this guy. The only thing I trust here is the public key of this certificate. And the signature inside here is signed by this one. And this one has signed this one. The sourcelens.com.au is signed by this. And that's how I am establishing the trust. It's just like you are meeting someone randomly in social media or anywhere, stranger, without any reference. You will not trust them. When you find out that he is a friend of your aunt's friend or something like that, you will establish that trust chain. That is exactly similar thing in this world as well. So these are the things I'm going to trust. These are like my family members, right? Whoever is trusted by these guys will be trusted by my computer as well. That is what is happening here. Now let's take the example of Wikipedia. You can take any example you want. Let's go to the Wikipedia for exploring the same pattern. Clicking on the lock button, clicking on connection is secure. Again, clicking on this particular icon here, the certificate icon. And again, the common name is star.wikipedia.org. Organization is Wikimedia Foundation. So that is the C name. We'll see what is C name shortly in this lesson itself. Now this is signed by DigiCert TLS Hybrid XYZ CA1. So it is signed by DigiCert. Now let's have a look at the chain. By the way, this is called a certificate chain. As you can see, it is a chain of certificate. This is signed by this, and this is signed by this, and this has to be in our root. If this is not there in the root, this whole thing will collapse. The entire chain will collapse. So let's have a check of this. DigiCert Global Root CA. So this is our certificate store, and we are looking for DigiCert Global Root CA, and it is right here. DigiCert Global Root CA. Here it is. One of the things, if you want, you can do is that export the certificate and delete and refresh. You will get problem here accessing the website. Right now, I don't want to do that in the middle of a recording because I don't know what happens, because DigiCert and things like that is definitely used by a lot of these recording software and pretty much everything else in my system. And if you're not doing something important, you can try something like that. But make sure that you export the certificate before you're doing that if you're testing something yourself. Export, and then later, of course, you need to import in the trusted root. Otherwise, your system won't work. Because these certificates are literally the backbone of TLS. As far as the trust is gone from the system. Now let's come back to our diagram. So this is what we were discussing. So digital signature is an essential part of the certificate. Why it is an essential part of the certificate? That is a part where we established who has provided this particular certificate. And Eve cannot do this because Eve cannot prove that she's Bob, because she can't get a certificate from the certificate authority proving that she is Bob. Certificate authority is an entity which actually checks. We'll discuss how it is being checked before signing a certificate that indeed Bob is Bob. It does something like an identity verification. You can think of it like it goes to Bob's house and meeting in person, check his identity, and then only gives the certificate. And we trust the CA for that. In fact, there are certain cases they literally do that, what I just said, just like issuing a passport. Some of the banks has the green certificate. It has a lot of verification done before giving that green certificate. When you access that, you'll get a green on the top of the address bar in the browser. Not sure if I've observed it. Now we are going to discuss the concept of CNAME, another important field, or SNI for the matter. Both are kind of used for similar purposes. So let's revisit our objectives here. What we are trying to achieve at the end of the day. So let's enumerate all our objectives, and then we'll try to find solutions using what we have discussed so far. So let me erase this diagram. So TLS, so we have the client boundary, and this is the server boundary. Client and server can be Alice or Bob, whatever it is. And this is the public network right here. Now the first objective is to make sure that you are really talking to the server you are thinking you're talking to. So that is one of the main objective. There could be someone else here telling you that it is the server, say google.com. So how do we verify that it is indeed google.com you're talking to? So that is objective number one. Now, the next objective is fairly straightforward, making sure that the data communicated between these two parties is encrypted and no one can see what is being transferred. That part is straightforward. We have the AES, we have established a key, and then onwards we are using AES encryption on top of it. So that part is fairly straightforward. Now the more difficult part is making sure that you are indeed talking to this particular guy, google.com. Now what we have here is a list of trust or list of public key you trust. That list is there inside the client. So those are the main two objectives we have here. Making sure that we are talking to the person we are thinking we are talking, as well as rest of the people cannot see that conversation. Only the client and server can access the conversation. So those are the objectives. Now for the objective of recognizing the server, what we have here is the public key of all the root certificates. or public key we are going to trust. The client has it. The client operating system has that information when you install the operating system. Also, it is getting updated every now and then. So this is the trust store of the client, where it has the public keys, the trusted certificates, trusted root certificates is there in the client. Now, any information signed by this public key, you trust, you assume that document is correct. Any document, it could be a bank statement, it could be a letter, it could be a certificate. Any document signed, we have learned the signature technique in our previous lesson. Any document which is signed by one of these public key, in fact, private key, and can be verified using this public key, just like we did in one of the last session on digital signatures. You're going to trust that because this public key is known to the operating system. Now, in the case of certificate, the most important thing is the domain name or CN. For example, the CN of Google is google.com. That is what is being certified. The certificate, as I mentioned, has the public key of the server. Then it has the CNAME or CN. SNI is exactly same purpose. It's more of a practical choice in terms of CNAME, SNI. So we don't discuss that much. It doesn't add anything to the conceptual understanding of what we are trying to discuss here. What we are trying to certify here is that whoever is giving this particular certificate with google.com, provided that it is signed by one of the root certificate here, it is indeed google.com. That includes the public key as well. Very important. That includes the public key as well. The certificate has, let me write that down, the public key of google.com, then CNAME of google.com. CNAME equal to google.com. So this is a string. Let's ignore all SNI and all kind of details. Let's just focus on these two things, public key and CNAME. Let's assume that the certificate just has this two information for the time being. And of course the signature, the digital signature of these two entities, which means that this is the public key of google.com and the certificate is indeed coming from google.com. Who has certified this? One of the guys. So this signature there in the certificate, when you try to access google.com, is signed by one of the non-private keys so that you can decrypt using this public key right here in your trust store. Very important point. If you want to review this video again, just do it right now. Pause the video and think about it. This is the crux of verification. So the certificate you get, the information you get from google.com when you access google.com has two information. One is the public key of google.com and the CNAME. Both is signed. Both information has a signature associated with it. Assuming that this is just single document right here. And the signature is signed by one of the trusted entities right here. And the public key is already available in your trust store. That is another certificate in fact, but at the end of the day, it is just another public key. This public key is Google's public key, and this is the public key of trusted root certificate, which signed this particular signature right here. Because the public key is of google.com, if you are talking to something else, if you have encrypted the traffic using this public key, no one else will be able to decrypt it. Very important point. If you had verified and make sure that if this public key is of google.com, which is what you did by verifying the signature, the only party which can decrypt the traffic is who is having the corresponding private key, and that is google.com. So there is no man in the middle attack is possible as long as none of this encryption algorithms are broken. So you indeed know that you are talking to google.com. So there is an Eve here. Eve is saying that Eve is google.com. Eve has a lot of problems. First of all, Eve cannot get a certificate from one of these trusted entities with google.com. Why? Because these trusted entities will make sure that it verifies, it has verification mechanism that the google.com only has that particular certificate. They will not sign a certificate like this and give it to Eve or anyone other than the actual company Google. In fact, not everyone in Google can get that certificate as well, the private key of that certificate. We will generate all these things shortly in our next session when we do the practical of SSL TLS, how to generate a certificate and things like that. But the idea is that you cannot get a certificate signed by one of these trusted entities saying that your CNAME is google.com. You cannot do that in the world. Now, Eve can create her own certificate which is not signed by any of these trusted people, and Eve can say that it is google.com. But the problem is that the client is not going to trust that certificate because Eve is not having a certificate which is signed by one of the trusted entities. Eve is having either a fake CA which is created by Eve itself, or it is a certificate which is not signed by anyone for that matter. Now, what are the options Eve is having to cheat the client? The main option is to edit the trust store, add a fake CA to this trust store. That really works. If Eve is adding or changing the trust store of the client, Eve can fake that it is google.com. So PKI infrastructure is not more safer than editing the trust store. Trust store is everything when it comes to certificate verification. Because of that, only the operating system administrator normally has permission to edit the trust store of the system because of this reason. Now, let's discuss how a browser uses a CNAME when you access google.com. So where is the CNAME? What is being compared with what? All that kind of details. Let's have a look to understand the complete flow of SSL and TLS. SSL/TLS. Both are same protocol. SSL is the older name of TLS, older version of TLS. So again, I'm drawing the boundary of client and server. The middle part is always the public network, and this is client and this is server. Server say google.com and client is say Chrome. Chrome browser is the client, and in the browser I'm typing google.com. So this is the first action anyone is doing, https://google.com. Now the first thing happens is there is something called a DNS resolution happens. So there is a DNS request goes to the internet. So there is a router somewhere here, DNS request or DNS server, and it converts that DNS server to an IP address. And we get the IP address 1.2.3.4. Why this particular part is very important is because whatever is being converted, the browser or any HTTP client, any TLS client is going to check what is the domain name or FQDN used here. That is the CNAME it is going to check inside the certificate. So in this case, it is google.com. So let's draw that in a different color altogether. So the CNAME or the FQDN we put in the top of the address bar of the browser is google.com. So this is the string which is getting converted. This is a string. Google.com is a string which is getting converted by the DNS to an IP address. So the DNS resolution has done for this particular string. Browser knows that. Now all the SSL business starts or TLS business starts. Client will say client hello, all these things we have seen. Client hello with all the protocol it supports and all the cipher suite it supports, all that kind of things. And server, next step is the server giving its certificate. with all the other details which we discussed, which protocol it has selected, which algorithm it has selected, along with it is giving the certificate. What are the things inside the certificate? One is the public key and CNAME and signature. There are other things like SNI, like I mentioned. In fact, SNI is kind of more important than CNAME these days, because CNAME is not really used anymore. It is the SNI, but same purpose. It's just larger string and things like that. Public key, CNAME and signature. That is what the certificate's main content, at least from this discussion perspective. Now what the browser is going to check is this particular string right here is equal to this string. We put it in the address bar. Very important. First, it will check the validity of the certificate. We have discussed about that. Checking this signature and making sure that it is signed by one of the root trusted private keys, trusted CAs. It is signed by one of the root CAs. All that is said and done. It has a valid public key. Everything is good. Certificate is valid. What is next? Next is this particular CNAME is equal to this particular name right here. That is the next thing the browser checks. If that is valid, then only the rest of the thing is done. The processing of rest of the traffic. It will use that public key and encrypt and send the session key to the server. And then on, the actual encrypted traffic starts. So a couple of things happens here. So browser knows that whatever user has put in the address bar of the browser is indeed the certificate coming down from the server. If this is not matching, it means that something else is happening. This string has to have an exact same match, complete match of these two strings, CNAME and this particular bit here. So let's check that in a couple of cases. So again, source length, any certificate you can check. So what we have put in the browser is this particular string right here. As you can see, HTTPS, because it is TLS, and this is HTTPS, and this is a string. This is a string which DNS resolution has been done. Very important. If something comes after this, doesn't matter. So for example, there is a blog, there's an FAQ, nothing matters. Only till here it matters. Only this string matters. Anything after that doesn't matter. This is the domain name or FQDN. Now let's have a look. The connection is secure, and then we have the certificate and CNAME matches exactly. It's a very simple certificate. It doesn't have any SNI or anything like that. So it is a CNAME which is exactly matching this particular string right here. Now let me show you something which doesn't work. So dev.sourcelength.com. As you can see, it is complaining. There's no HTTPS and it is dev.sourcelength.com, which means that when I access this particular URL right here, I didn't get a proper certificate. It could be anything. The certificate is not there, or the CNAME is not matching, or the thumbprint or the hash is not matching. The verification failed. Could be anything. So let me go to advanced, continue to dev. So this is our dev. Basically, this is a playground. It is not the actual website. So not secure. Are we getting any certificate? I don't think we are getting any certificate at all. Let's see if anything is coming. So some parallels, some default certificate is coming. The CNAME is parallels panel. It is some backend service that server is using. It is giving some default certificate which is not matching. The CNAME is not matching. So this is the CNAME. We should have had this particular string right here. Let's see if it is a valid certificate. It's not even a valid certificate. So there are multiple reasons for the failure. First of all, the CNAME is not matching. Also, it is not signed by one of the trusted entities. So this certificate, I'm pretty sure it's not in my trust star. So we will see some of these permutations and combinations when we do the practical of TLS. So let's go to google.com and see the certificate. So this is a more complicated advanced certificate which has lot of things, should have a lot of things. So star.google.com, first of all there is a star here, which means that anything.google.com, this certificate will say yes to it. Say anand.google.com, this particular certificate will work. And let's see the details. Let's see if it has any SNIs. So it is having a proper trust root. Subject and CNAME is exactly same thing. Another very important field in a certificate is the validity of the certificate. Always, all the certificate has a end date, not after. Very important. Then of course the issuer of the certificate, who has signed this certificate, and all the algorithms, signature algorithms and things like that. What we are looking here is that if it has any SNIs. So for some reason this browser is not showing me all the information. So that is another thing with certificate viewers. Certificate is just like any other document. When I say document, I mean like image, like a JPEG file or any other file, text file or anything like that. Different file viewers will give slightly different results. Certificate is exactly same. I'm not seeing the SNI. I'm pretty sure Google has SNI, but this is not showing me that. Right now I'm using Edge. This is an Edge browser and the certificate viewer of that Edge browser. Let's see another browser. Say Mozilla. So I'm in Mozilla right now. Let's go to google.com. and let's have a look at the certificate. Mozilla has a little more information normally. So this is the certificate. Let's have a quick look at what we are looking for. As you can see, there are a couple of details here. TLS AES 128 GCM. So a lot of these algorithms are there, TLS. So these are the algorithms and cipher suites it is using. TLS 1.3, which is almost the higher version of TLS at the time of this presentation, TLS 1.3, and it is using AES with 128 GCM. It's again a algorithm, SHA-256 for hashing. All that kind of details is there. What we need to look is the certificate, view certificate, and subject name star.google.com, that is there. This is the issuer name, which is there now, trust store, and this is the trust chain. Here we go. This is the subject alt names, or SNI or SAN, both are same. So which means that these many names are certified by the certificate, which means that all the Google products are using pretty much same certificate. For example, even if you go to google.com, probably you may get the same certificate. Let's see that. youtube.com. Let's see if we are getting the same certificate. So connection is secure. More information. View certificate. Is it the same page? Looks like it is the same page. How about that? Interesting. Not sure you understood what I just did. We just simply proved YouTube and Google is using exact same certificate, which means that if you get one private key of this particular certificate, you can shut down an entire organization. I'm pretty sure Google is keeping that really safe. Interesting. So let me repeat what I just did. So first I gone to google.com. Let's do that. So this is google.com. Let me close this thing so that there is no confusion. And I clicked here, and then I clicked here, more information and view certificate. So that's what I did right here. Then I got this particular certificate right here. Now I'm going to do the exact same for youtube.com, and connection is secure, more information, and a view certificate. As you can see, all this is exactly same view certificate, and I got the exact same certificate right here. The reason why it is using the same certificate is because all the Google products are there in the SNI. SNI is exactly same use as CNAME we discussed. It's just that you can mention any number of SNI in a certificate. What Google has done is both secure and insecure in a way, because like I said, if one key, there'll be a single private key for the certificate somewhere sitting in the network of Google. I'm pretty sure it is in a hardware HSM or something like that, but there is one private key for the certificate, 100%. And if that one private key is compromised, all of their products is compromised. As you can see right here, everything is there in this one single certificate. Probably it is secure in a way that they must have done all the cares which is needed in the whole world to make sure that this one single certificate is as secure as possible. For example, if there were 100 different certificates for this 100 different URLs, the management would have been more difficult. I'm pretty sure it is a conscious decision Google has taken to do what it is done. So being said that, as you can see, all the products from Google is using same certificate. Most of the organization which I have worked, it's not a case. Normally it is different certificate. So that is the use of CNAME. Whatever you're putting here in the address bar should be there either in the CNAME or in the SNI or SAN, the exact same string. Normally this www is discounted, but almost all the names in Google has a star in front like this, so that www is discounted. So that is the summary of TLS. Now, one more thing worth mentioning here is the MTLS, which is exactly same as TLS, but one simple and single difference. Again, let me explain it with the help of the boundaries. So this is the client, public, and server. Now, the client is saying client hello, server is giving the certificate, and optionally server can ask for the client certificate as well. So right now, so far what we have discussed is verifying the server. What about the client? In 90% of the cases, client doesn't care, or server doesn't care about the client certificate. Client doesn't matter. It is the server which matters. For example, google.com. You need to make sure that you are connecting to google.com. Google doesn't care who are you unless you are authenticating into one of their services, in which case it has other mechanism like username and password. But otherwise, in the case of TLS, transport layer, it doesn't matter. But in certain cases, the server has to identify the client. In fact, MTLS is an option for username and password. In fact, it is a slightly more secure option. It is very tedious to maintain, but it is a slightly more secure option instead of username and password. And the concept is called MTLS, mutual TLS. MTLS or mutual TLS. So mutual TLS, just like the name says, after the client hello, server respond with the certificate. So this is the server cert, and server ask for the client certificate as well. So the client has to give the client certificate. Otherwise, the connection will be broken. The handshake will fail. By the way, this thing is called TLS handshake. We will see some articles and things like that where we get into the exact jargon of all these stuff. But otherwise, this is called the TLS handshake. So if the server needs the client certificate, and if the client certificate is not optional, then the TLS handshake will fail. So why we use MTLS? We use MTLS to make sure that the client is also important in terms of whom it is claiming it to be. So the client will have a CNAME and server will verify that CNAME, just like it verified the CNAME in the address bar. So we'll see an MTLS example as well in our demo, which is coming in the next lesson. But the concept remains the same. Like the server is being verified in the normal TLS, the client is also verified by the server in MTLS. Now, let's have a look at certain articles and things like that to make sure that we got all the details which is required. Also, feel free to look at more details about certificate. There are other fields inside the certificate, but important fields, the signature and the public key along with CNAME and SNI. Those are the important fields. There are other fields like expiry, the duration, all those kind of things. So have a look, because certificate is the entire data within that file, including the other things. So I'm going to type TLS protocol details in Google. Let's see what this particular website says. Cloudflare, a lot of documentation is there. If you want, you can read about it. So let's have a look at the diagram. So this is the TLS handshake. SYNAC, ACK. If you're new to this thing, feel free to refer to my networking training, very important. So this is the TCP handshake, SYNAC, ACK. This is the connection oriented protocol, TCP, because it needs all the acknowledgement and sequence number that is being set up here. Not going into the details. If you want to refer, please refer to my networking training. And this yellow part is where the TLS handshake begins. Client hello. Client hello has all those details which we mentioned, cryptographic details. And server hello, server certificate, server hello done. All this is happening here. Server certificate is being transferred. Now, using all these details, client key exchange, change cipher spec. So this is an important phase transition in terms of TLS. So till here, the connection is not really encrypted. Since SYNAC ACK is definitely not encrypted, anyone can see, anyone can modify, doesn't matter. Client hello, not encrypted. Server certificate, not encrypted. But from then on, once it has the public key of the server, it starts the encryption. First, it creates a random symmetric encryption key and then switch. This switch is this change cipher spec. That's where the things changes. Encryption starts. From then on, no one can see the traffic. Change cipher spec. And then once the server has the key, the symmetric encryption key, server also switches to change cipher spec. So from here onwards, from server side, whatever server is sending will be encrypted. So this article is good. It is discussing about performance and things like that. And this is the URL of this particular link if you want to note down. A lot of details are there. Looks like it's pretty good. I'm reading it for the first time, but essentially everything should be same. TLS Wikipedia page should have a little more details. Normally Wikipedia has a little more details, although it's not very organized. So one of the things you can look here is the SSL 1.0, 2.0, 3.0. Then it's not 4.0, it is TLS 1.0. But it is just the later version of the same protocol. And 1.3 is the latest. It's been a couple of years. 1.3 is there. Hopefully it'll be there for some more time. So very detailed changes. So one of the things they have added throughout this series is that they are checking the unencrypted traffic as well. They are making the checksum of the unencrypted traffic. Let me go to the previous article, the one from Cloudflare, to explain what I'm talking about. This is the detail. If you don't understand what I'm going to say, just ignore it. Not very important. It's one of the things they does in the later version of TLS. As I said, these packets, for example, the client hello server certificate, these packets are not encrypted. But client knows what the information it has sent before the change spec finished. Before the encryption, client know what it has sent. With that information, what it can do is that it can verify with the server by sending a checksum to the server, encrypted checksum to the server that, hey, I have sent this much data. Did you get it? This was the hash of the data I have sent to you. Can you calculate that hash? And making sure that there is nothing in between. So this is like a encryption or verification, not encryption. In fact, verification of the past data client has sent. Previous version of the SSL didn't do this particular step. Later version does this. I think it has started to do that with TLS 1.2 or 1.1. Not really sure, but that's one of the important changes in the later version of TLS. Which means that the connection will be broken if someone has tampered with client hello or server hello, even though it is not verified at the time of the packet which is being sent. It is verified in the future time frame. So going back to the Wikipedia article. So versions of TLS is here. TLS 1.2, 1.3. So digital certificate we have seen. Certificate authority at the end of the day we have discussed in length. It is just a list of public key we keep and we trust. Whatever is signed by that public key, private key pair, we are going to believe that information. We're going to trust that information. That's the idea. So encryption, authentication, integrity, all this cybersecurity jargons are there associated with the certificate. Different algorithm and different versions of TLS. Have a look at the article. Pretty good. It is talking in length. One problem with Wikipedia article is that it's not very organized. Probably this is an interesting part. The attacks. So read about the attacks. If you want to really know the protocol, attacks are the single most important source of information. So this is the TLS handshake right here. It's a little more detailed. Client hello, server hello with the certificate. It is in fact pretty much same as that Cloudflare thingy we have seen. Don't want to get into the details. After the change cyberspec, we can send any amount of data through that session and we'll be using the same session key. This article is pretty huge. Let's see one more article. This is from IBM. There's a specific article for TLS handshake. Doesn't have much details. Pretty much everywhere it should be the same information if you have. There is one article though I have found interesting. I'll give that link in the description of this particular video. Let me show you that link. So this is the URL which I was talking about. If you want to search, probably you can search something like traffic analysis of TLS session. This is the website, gitlab.io. It's like a blog of someone, but it is pretty good details, more details about the TLS handshake and things like that. But hardly in our daily life we'll have to deal with it unless you're working on some kind of attacks and things like that. A little more detailed. We are not going into the details of all the bits and things like that, but there is a lot of bits and byte level information. I'll put this link in the description of the course, or you can just take it from here, or you can simply search this thing in Google. Should come up this particular link in case if you want to have more information. But all we need is what we have discussed in 90% of the scenarios. Now we will do some practical using OpenSSL and simple web server and things like that. Otherwise, all we need is the details we have so far discussed. So we have seen the basics of SSL and TLS, but there is more to it. We need some more practice, demos, and a lot of other details around it. So let's get into it in next few chapters. Thank you and see you in the next.